Okay. Okay, welcome everyone to the DDPS seminar. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me introduce our speaker today. It is an honor to host Ajay Harish, who is an assistant professor of engineering, simulation, and data science in the Department of Mechanical Aerospace and Civil Engineering at the University of Manchester. Prior to arrival at Manchester, Ajay was awarded a bachelor's in mechanical engineering from NITK Suratgarh at India, and master's degree in aeronautics from Caltech in US, and a doctorate in the mechanical engineering from Leibniz University, Hanover in Germany. And he was back in California for the postdoc at the Naval Sim Center at UC Berkeley. His research group at Manchester develops numerical methods for uncertainty quantification for application in modeling waterborne hazards problems like storm surge and tsunamis. Today, Ajay will talk more about the uncertainty quantification and deep learning for water hazard prediction, which will be very interesting topic. So please enjoy and expect a wonderful talk. Now, without further ado, let me pass the baton to Ajay by asking one random question as usual. Today's random question, it's not a random question. The same questions we've been asking. What is your favorite thing to do other than research? Especially in weekends. What do you do in weekend?
Currently, I'm spending weekends writing grants, but I think that's not. I wouldn't say that's the most favorite thing to do. I played a violin, so that's kind of, let's say, something that I would enjoy doing.
Oh, that's lovely.
If I get a little more time, I would say so. Yeah.
That's lovely. That's lovely. Okay, stage is yours.
Thanks, Yunsu. Thank you so much for the introduction and for the invite for the DDPS seminar. Today, I'll be, as Yunsu said, I'll be talking about some ideas about uncertainty quantification, particularly related to water hazards and waterborne hazards like tsunamis and storm surges. And anybody in California is probably not new to these events, like so, especially tsunamis. Somebody on the East Coast definitely has heard of storm surges. Especially there's a recent Ida hurricane there, which created quite a bit of devastation in a way. So I'll try to focus a little bit on the physics of the problem as well, just to highlight because not everybody might be aware of how these events are modeled and how are we looking at it and what are the different scales and things like that. Before I go ahead, I would just like to give a brief general introduction about some of the work that's done in my lab. So this is the overview of today's talk. So what is just the overview of what we are doing in our lab here in Manchester. Then about Naval and Sim Center, a lot of work that I'm talking today was done at UC Berkeley, and I'm continuing on that. And so this is one of the directions. We recently submitted a grant to look at debris loading on structures and so on. And so what are these waterborne hazards and why are they important? Probably I don't have to stress on the why. So what are the modeling techniques and how do we do the uncertainty quantification in there? So it's a very high dimensional problem, which makes it really difficult to do anything in here in a way. So, and as we go ahead, you'll see what are the difficulties involved, and I would definitely welcome more ideas, and I'm open for discussions in a way. Right. So just to give an idea of what we do in our lab, there are two things. One is the application side of things, looking at different applications like storm surges, tsunamis, waterborne hazards, fluid structure interaction problem. At the moment, I'm also looking at biomedical problems related to neurovascular blood flows. And on the other side, we develop methods that can be used in there. There are a lot of methods already there. And how do we improve these methods? How do we make them better? How do we especially look at code coupling in a way? How do we couple different methods to look at their advantages. For example, we are trying to couple at the moment material point method with finite volume method. Material point does very good with regard to large deformations in structures, but then it has a lot of integration issues when you're looking at flow problems where finite volume does very well. Can we couple these methods to, let's say, do more robustly? And of course, big part of it is uncertainty quantification and machine learning as well to accelerate some of these simulations with surrogate models and so on. So some of the application, the one thing that we are looking at is tribological applications. There are a lot of emission standards out there for exhaust emissions, or when you say exhaust emission, anything coming out of a tailpipe. And especially with the push for electric vehicles, I think this is something that's going to go down. But what has not been classified or like kind of characterized well is non-exhaust emissions. So this is something related to tire wear and brake wear. I mean, it doesn't appear like a very, let's say, appealing problem to look at. You know, who cares about the tires in a way, right? I mean, that's kind of like somewhat the attitude that's there with a lot of industry as well. As long as the tires last for a while, we don't care. But then a big problem is all the PM 2.5 particles and PM 10 particles. That's a significant contributor to it. But then there are no emission standards that really regulate these kind of particle sizes coming out of it. So that's kind of something where we are looking at. Also, we do some bit of traditional mechanics related to contact mechanics. For example, there's just an example of what is called as a flying spaghetti problem. So if you have spaghetti and just drop it down, how is it going to like fold around? And it's again a 2D problem in a way. Or looking at contact mechanics between very flexible bodies and slender structures, or even 3D contact, which kind of has applications in tribology and so on. I mean, tribology, if you look at it, there's a lot of uncertain parameters in there, right, from the road surface to the material model. So it's extremely high dimensional uncertainty quantification problem that to look at. And one of the recent applications of us has been to look at data-driven modeling in looking at carotid and stroke-related issues. How do we quantify the risk of a patient? For example, when a patient comes in, they either come in, they look at it, they say, okay, probably the patient needs a surgical intervention, or they go back and probably they come back again for a surgical intervention, or it's pretty much late. So how do we kind of say that, okay, this patient has a high risk for a stroke and somebody does not have a high risk for a stroke? So where we are combining fluid mechanics simulation with deep learning techniques and Bayesian neural networks in order to quantify the stroke between different patients and predict some form of a risk in a way. A new thing that we started out was to look at the cerebral flows, especially regarding the neurodegenerative disorders, and to look at the oxygen level. One thing that we can easily image is the larger capillaries, but we cannot image, larger arteries, but we cannot image the smaller capillaries and veins. And one of the difficulties that many of the, let's say, very hard to do automatically with a neural network is to be able to decipher between what's the artery, what's the capillary, and what's the vein in a way. So can we automatically use neural networks to build these vascular structure in our brain and look at oxygen levels and eventually look at how this lack of oxygen degrades the brain tissue and so on. So this has been a new work that we started. It's just our start, a work in progress. But just to give you an idea of it, apart from the natural hazards, one of the other areas that I'm looking at is biomedical problems where there's a lot of uncertainty quantification to think about. In a way, right? So just to start with, a lot of this work that I'm talking today was done with the Naval and Sim Center at UC Berkeley. So just to give an idea about them, because without talking about them, this would be very unjust to the contributions that come from NARI and from the Sim Center into this work that we have done. So NARI is a network of natural hazards engineering research infrastructure. So it has several experimental facilities. For example, like there's a wall of wind in University of Florida, the large wave flume facility in Oregon State University, and so on. There's earthquake in UC San Diego. These are, I think, at least the ones that I had interactions with. And there's several other also experimental facilities that contribute into different natural hazards. And Sim Center is the let's say, computation modeling and simulation center, where we were developing, or we're continuing to develop a lot of computation infrastructure that goes into these softwares to simulate natural hazards and so on. So the goal of the Sim Center has been to build a very modular open source framework. So you can go to the GitHub. All of this is available on GitHub, all the work that we do, where we have built it in a very modular fashion. For example, how do you characterize the assets? For example, like the building infrastructure, how do you get the information about that? How do you characterize the hazard, like tsunamis and storm surges, earthquake, and wind hazards, and so on? And how do you eventually come out to the response of it? How do we build a more resilient infrastructure in a way? Of course, a lot of this started with looking at earthquake. So Sim Center is currently in the second phase of the funding from NSF. In the first phase, a lot of initial focus was on the earthquake engineering. So that's where a lot of uncertainty quantification also started with. And eventually this has been adapted also for the water-borne hazards and the wind-borne hazards and so on in a way. So what we see here is essentially, I think we should find some pointer here somewhere. Okay, so what we are seeing here is in the red box here is what we call the COFEM, and COFEM essentially is the couples the uncertainty quantification with finite element, and eventually all of it is runs on a cloud, which is a TAC supercomputer in Texas. And Hydrouq essentially uses along with it, brings in tsunamis and storm surge inundation and CFD as well into the fold. So the whole idea is to combine earthquake, which is the EUQ, VEQ is the wind, Hydrouq is the water, and give a probabilistic assessment through PBE and R2D. So where people can use that to build more resilience-based decision making and so on. But today we'll focus on this one thing called Hydrouq and look at how these waterborne hazards are firstly modeled. And second thing is what are the uncertainties that come into these modeling these events, and how do we account for them in a way, right? Okay. Okay. So I think most of you would be familiar with tsunamis. A big one that happened was in 2004. Where there was severe damage to ports and coastline. A lot of these damage happens because of the debris. For example, here on the bottom, we can see the Indonesia coastline before and after the tsunami. On the left side is before, with a lot of tree cover and so on. On the right side is right after the tsunami, where everything has been washed out. A lot of these debris have like less than 10 meters per second speed, but then they can be very, very damaging when they kind of crash into into the building infrastructure and so on. So the tsunami basically killed about 250,000 people, and it's a magnitude of 9.2. We understand the largest wave was about 30 meters, or like about 100 feet. When the tsunami hit, and so that's essentially kind of washing away literally anything on the track. So one of the things that's very important in these kind of events is to build vertical evacuation structures that can resist these kind of loads, because a horizontal evacuation in these events is almost impossible to think about. So people try to do a horizontal evacuation, and that doesn't happen. That eventually leads to loss of life and property. But then if we can build large evacuation structures that are vertical in nature, that could probably save a lot of lives. I mean, same thing happens. For example, these are like this 2010 Chile tsunami, where there's again a lot of damage to the port, where these shipping containers and ships, as you can see, moved into the port. These ships have very, very small velocity at this point, but eventually they have a large mass, so they're bringing in large amount of momentum that can really destroy these infrastructures. So eventually, we want to make sure that these infrastructures can withstand the loads that are there, and they don't get damaged in a way. Right. So this was very interesting event that not interesting, but then very important event that was missed quite a bit during the 2011 Tohoku tsunami, where there were supposedly two submarines inside this port. And these two submarines, when the water entered in through the port, these submarines were basically rotating around there. as the water left through it. So there's not much damage, so they did not come up into the news, but that could be a very significant, important thing to account for on where these ships and submarines can be parked and how to account for these kind of hazard events and so on, right? So, and the similar things happens during the storm surges. For example, there's oil rig that happened in 2005 during Katrina storm surge, and so you can see the oil rig before and after. There was significant amount of damage, and so this was a Category 5 hurricane. This was very similar event happened with Hurricane Ida recently on the Mississippi, where the river started flowing backwards for about 2 hours from the Atlantic Ocean. So instead of flowing into the Atlantic, it was flowing outside back into the land for about 2 hours, and then the flow was restored. This was in the storm surge. It's not just the water waves, but also wind that adds an additional damage that can create a lot of wind debris that can really damage these infrastructure and so on. So essentially, we cannot let's say stop these events from happening, but then we need to build our infrastructure that are resilient and that can account for these kind of events, and that automatically says that we need to account for different range of events. It can be a small event, it can be a large event, but it can be once in 100-year event. But then how do we account for these things? And that's where UQ comes into the picture, as you'd already guessed in a way, right? So just to give an idea for what's the storm surge and how does it happen, one can think about it that there's a center of low pressure around which all the water is being drawn, and as this low pressure area moves towards the land, this water is kind of pushed towards the land. So people can expect about 15 to 20 meters, 20 feet of storm tide very easily. And again, this depends on the magnitude of the event and at the low pressure area and so on. But even during storm surge, one of the biggest thing is also the wind-driven surge, and also the wind-driven debris and damage that kind of come in along with the storm surge as well. So there are two kinds of tsunamis as well. I'm going back and forth between storm surge and tsunamis because though they are different kinds of events, eventually at the end of the day, when it comes to modeling, very similar approaches are taken for both of these events. And so as we will see later on, if you look at what causes a tsunami, one is either like you have a seismic event, which is an earthquake, so the motion of the fault. So if roughly crudely to think about, you have something of ocean floor that suddenly moved up, which means a whole block of water has moved up, and now you suddenly this block of water has to go somewhere, and it kind of moves towards the land. And the second thing is landslide, which we never think of that to be creating a large magnitude tsunami, but these are highly localized tsunami. And one of the largest tsunamis where there was over 400-meter wave was in Alaska in 1958. So these are very localized events, but then these can create a lot of damage in that particular region where there's a huge landslide that is happening in a way. Right? Just to look at some of the modeling approaches. So please let me know when I'm running out of time.
Yeah, I will do that. Yeah.
So thank you. So just to look at some of the modeling approaches, because that kind of makes it important to understand how do we put UQ into the problem? What's the problem in there before we can put UQ into it, right? So just to, most of you would have done a wave mechanics course, and so I don't have to talk about this. A wavelength, what's the crest, what's the trough, what's the wave height and wavelength. So right, so but then just to get us all on the same page, right? So we have two crests, and distance between them is the wavelength, and distance between the trough and the crest is basically the wave height, right? So one of the things is essentially what happens with these kind of events like tsunamis. They're very long wavelength. So in the ocean, in the deep ocean, you will never recognize that a tsunami is coming in because the wavelengths are very long compared to the depth of the ocean floor. So, but then only what would happen is, as these things, is a very crude image of what would happen as the wave moves towards the shore, the depth of the ocean floor is starting to reduce, which means that this energy that is coming in has to go somewhere, and the height of the wave eventually increases. And that's what leads to a lot of devastation in a way, because as soon as it starts to meet the ocean floor, the wave starts to slow down. And once it starts to slow down, the faster moving wave starts to crash and it starts to break in a way, right? So crudely to think about, this kind of leads to a lot more devastation because of wave breaking effects and so on. That itself is a lot of interest to the community. So the modeling assumptions that are often made, and one is that the floor is incompressible and inviscid. The amplitude of the wave is much smaller than the wavelength and the depth of the ocean. The flow moves over a complex bathymetry or topography, so the ocean floor is pretty complex. And one of the things it evolves over multiple length scales, right? So in the ocean, open ocean where you have kilometer resolution, but then when they come to the near the coast, you need to look at a meter resolution. As we'll see some of the results later on, you'll see that we need adaptive mesh refinement in order to account for different sets of grids that are there, both in the deep ocean and in near the coast in a way, right? Okay, so this what we did. We developed this tool called Hydrouq that combines the ideas of that brings together, let's say, 3D finite element, 3D computation fluid dynamics, where we use open source tool OpenFOAM, and we brought in shallow water solutions. As you will see later on, how all of these things are combined. So, but just to give you an idea, so most of our infrastructure is coastal infrastructure, which is at risk. For example, it can be looked at as these buildings that are highlighted in these yellow colored boxes. And so these are our buildings of interest. Either it could be an offshore structure or it could be a structure right on the coast. And there could be either a fault or a low pressure zone that is driving the water. And that would be our domain of interest for our 2D shallow water solution. So if you want to do CFD simulation over a large domain, then you really need a huge computation resource. I don't even know if it's possible. I've never tried it personally, but maybe people do it for meteorology. People from meteorology do these kind of simulations. But in the most of the community, since these waves are more shallow water waves, the shallow water 2D shallow water solver is used in the deep ocean. But as you come into the coastline, you need a much more high fidelity solution. Though these shallow waters can capture the inundation heights reasonably well, they're not so good at capturing the forces on these structures, which is kind of what we want to look at the building response eventually, right? And so there we combine this with OpenFOAM or like any kind of a 3D software, and the building itself is looked at with a 3D finite element and some uncertainty quantification, looking at the building response. At this point of time, we were not interested in looking at what is the let's say like uncertainty in the event itself, but more like what would be uncertainty in the structural response for a particular event eventually. So eventually that the idea would be also to become combined to like looking at uncertainty between different sets of events in a way. And that makes it harder because the looking at 3D CFD with uncertainty quantification makes it very time consuming, and that's kind of where 3D FEA is really fast. So essentially coupling uncertainty quantification with that is much more easier and more computationally efficient than doing it with 3D CFD, full fidelity CFD in a way. Right? So just to give an idea of depth average Navier-Stokes, so we have like basically the Navier-Stokes equation, which is our momentum conservation and mass conservation. And what we start by doing is looking at, let's say, if we start to neglect y, our component, and let's say y is our depth, we start to neglect that, and we start to look at it as a 2D problem. Let's say, or like no, we just start to look at it as a 1D problem. Let's say z is our depth and x is our one direction in which the wave is propagating. Then we can reduce our Navier-Stokes and our mass conservation to one less equation in there. And now what we want to do is we want to couple everything with our boundary condition. So we have a free surface, which we call eta, and bottom surface as b. And we can say that we can kind of couple our velocities. We can say that our velocities at the bottom surface is maybe is 0, and the pressure at the top surface is 0 essentially. So we use our boundary conditions, and we can always generalize this into 2D. We started what we need to do is we need to integrate over the depth, right? So and I've just shown it a 1D in a way, but we can always add the y component to it, which will give you an additional equation in there. Dou u by dou x is nothing but in the x direction, and y direction would be on the other side of the surface, other direction of the surface perpendicular to that, and that is our depth that we are looking at. Primarily what we want to do is we want to integrate over the depth, right? So we are integrating b is our bottom surface or the ocean floor to eta, which is nothing but our let's say our free surface. So once we are able to integrate over from bottom surface to the top surface, take our Navier stokes, all of this reduces into a much simpler form, which is looking at how is the variation of the height with regard to time, and what is the variation of they say height is essentially our bathymetry, they say the height of the water column at that particular time, at a particular point, and u bar is nothing but the depth average velocity at that particular point at that particular time. So both are function of x comma y and time, and h is nothing but the water column, which is kind of changing as you would expect, right? So this, all of these leads to a very nice assumptions that leaves us with a 2D equation to solve on the shallow water front in a way. So again, we can always increase that, and we can write it in a very nice form for our steady state, where we can say our steady state ocean is represented by the H is the water column height and B is the location of our bathymetry. So we define a mean surface, and with regard to that, we can say that is equal to 0. So 0 is our mean surface when the ocean floor is at a steady state. So that accounts for, let's say, any kind of variation that is there over the water, right? So I'll skip a couple of equations here, but we can come back to that as we progress through the seminar. We can come back and have a look at these equations in a way. So what happens during a tsunami initiation is that we are just saying that our free surface has changed by some amount. So we say that eta, which is our free surface, is no longer at 0, which is no longer at a steady state, but the height of the eta, which is our free surface, has changed to some amount, and automatically this d eta by dt progresses over the entire set of equations in a way, right? Okay. So all of this leads to a very nice set of hyperbolic equations on shallow water that we need to solve. One of the things that has to be done is we need to discretize when we take a 2D domain and we need to discretize it. We have to divide them as like a wet cell and a dry cell. So that is what makes it a little more complicated. A wet cell is where there is some water, or the height of the water column is non-zero, and a dry cell is where the height of the water column is 0. So because we are taking the bathymetry of the ocean floor, but we also are taking the topography of the land overall. And now as the water progresses, it can move from one cell to the other in a discretized state, where our mesh can change from a wet state to a dry state, and dry state to a wet state. So there can be states which are always wet, which are always dry. This is the land and the ocean. But then the coastal region would always change between a wet state and a dry state, and that needs to be accounted for when we are looking at the ocean floor. So just to give you some examples of here this hypothetical magnitude 7 earthquake. So I wouldn't say there's an earthquake that happened or there's something that's going to happen, but there's a hypothetical case. So I just want to be careful on that. On the Alaska fault, so where we are looking at 2 points of interest. One is the Crescent City in California, and the second one is Honolulu in Hawaii. And there's adaptive mesh refinement that has been used from level 1 to level 6. So this is what I was saying, that when we are looking at a particular region, let's say on the ocean, then we are looking at a level 1 grid, which is very unrefined. And when we are looking at some kind of a coastal region, then you need to refine this area so that you can get a much cleaner and better resolution, let's say, results on the coast where we are trying to look at these events. So this grid size, just to give you an idea, 1 degree is about 110 kilometers. That is about the grid size on the ocean, in the deep ocean that we are looking at. And and when we are looking at near the coastal region, we are looking at about half a second, where the grid resolution is about 15 meters. So that's just to give you an idea of the different grids that are being used. And this original case was run in collaboration with Professor Patrick Linnett at USC. So this was done when I was there at UC Berkeley. Right? And there are 2 regions of interest. One is the place in Honolulu, and one is the coastal region in Crescent City in California. And so there's just a visualization as the wave progresses. What we are looking at, the red and blue, is essentially the trough and crest of the tsunami wave that is propagating in a way. So this has been, as we'll see later, even though the scale is between 0.2 to minus 0.2 to plus 0.2 meters, that's because that's the, let's say, the wave amplitude that reaches Honolulu in Hawaii, but then in Crescent City, that's more than 6 meters, as we will see in a couple of minutes from now. So as you see, I don't know if you observed, but probably it's something that we can go back and again look at it, is if you look at this is the 110-kilometer grid, as you see there. So the grid is extremely, there are furthermore cells in there, but then there's just the outline so that it doesn't look very bad. The grid is extremely, let's say, sparse in a way. It's not dense, but as the simulation progresses, there's adaptive mesh refinement that is there in GeoClaw. So most of the simulations were done in GeoClaw. You can see near the Crescent City and again near Honolulu in Hawaii, these smaller grids are there. So this is not exactly a level 6 grid that you are seeing, because level 6 grid would be much more dense in there. So these are like the much more smaller grids that are used near the coastal region in order to get a much more refined solution and much higher accuracy with regard to inundation depth and so on. So again, just to look at the level 1 grid for the entire basin, this is what we were looking at, but that's something that was imposed on Google Maps. Again, we can see that the different levels of grids come into picture as and when the wave propagates in there. So these cells are essentially like a wave, wet or dry, that I was showing in there earlier. As the wet or dry kind of changes, these additional grids that are there are adapted by GeoClaw automatically. So this is a level 6 grid in Crescent City in there. At the can you see? Okay, yeah. So initially, when you start, this level 6 grid is just one big cell. It's not been there, but now as the water flows in, you can see that it really adapts in there to give a much better resolution. So now all this is much higher level grid that you can see all the different coastal structures that are there. So as the water progresses in, these additional grids take over in order to give a much better refined solution for the problem in there. Yeah. So this again like at Crescent City, where we can see this is basically a cross section area of the Crescent City that is there, where we are looking at the water progression, and we can see that there's one wave coming in. So there's a second wave that goes up to 6 meters, and there's a third wave that's about a little more than 2 meters. So if we go back to see that, so we can see looking at the water level series, we saw that there was a small wave coming in, and then there was a wave that went up to about 6 meters, and then there was a third wave that came in. So it's not just one single wave that comes in during the event, but then there were multiple waves that could come in at different levels. Again, if we go back again to Honolulu to look at it, we can see the same kind of an event in a way. But then here, as you saw, the wave amplitude was much smaller, and that was the reason why in the original video, the wave amplitude was kept at 0.2 meters. So you can see everything is really red, but doesn't show much of an event here. Yeah. So this again, like if you look at the water level, this is between about -2 to -0.2 to +0.2 meters in a way in Honolulu, while about 6 meters in Crescent City, California. Right. So these are the kind of modeling techniques that are used during these simulations. So we are looking at primarily like shallow water simulations in order to be able to get these inundation depths. So first thing is we get the inundation depth, but second thing is what do you do next with this inundation depths, in a way, right? So we need to take these inundation depths and somehow feed it into a CFD software. So what happens here, we have a 2D grid, which is essentially a nice square grid on our between a certain latitude and a longitude. But now in a 3D simulation, you have essentially like a face that goes through the entire ocean bottoms, ocean bathymetry in order to account for it. So there needs to be somehow conversion, which in some solid mechanics sense, it's basically like somebody's coming from a solid mechanics background. One can think of connecting a beam or a plate to a shell, or a beam or a plate to like a solid in a way. So you have a 3D object to which you have a 1D or a 2D object that's connected. So there's essentially the same kind of physics that needs to be accounted for when we are interpolating between a shallow water solver into a CFD. So in a way, we have a depth average velocity information that needs to be converted into a full 3D velocity to input into a CFD tool in a way. So Hydrouq does these things. It takes the input from the 2D water shallow water solution that we were discussing and inputs it into as a boundary condition into 3D open foam in order to run 3D CFD simulations. So once these 3D CFD simulations have run, so that gives us some forces and forces on our structures, and that's where we had at that point of time we had a focus to look at the uncertainty quantification in these structures. So a lot of work also has to I have to credit to Sangri and Akash, who also did a lot of work on the UQ methods that have been developed, and they're still currently at the Sim Center who have been working on the UQ methods as well. Right. So what did we want to look at? So first thing is we wanted to look at what is the propagation of these uncertainties from inputs to outputs, right? A simple thing to think about is, let's say we had some kind of original design, but then there needs to be an alternative design because of the different displacement that these designs would lead to in a way, right? So which design should we select? So that's where uncertainty quantification comes in. And what are these building structures? What are the responses from these building structures? Looking at these kind of fluid loads that are coming in, and particularly looking at some of these debris loads that are coming in as well, right? Okay. Yeah. So two big things as I was discussing with Yungsu right at the start was one of the biggest thing is if there's a damage to infrastructure, what is the repair cost and what is the downtime? And that's one thing that has been seen is these flood events significantly affect more marginalized communities in a way, and how do we make the impact a little lesser in a way? So we want to understand the overall uncertainties in our inputs and how do they how do they let's say uh, propagate through the system in a way as the outputs, and kind of looking at what would be the repair cost, downtime overall in a way, right? So we want to do all of these things, and the simplest thing to start out with is to say, okay, what would be the Young's modulus of this structure to start with? Let's assume that this structure is made of a steel structure. What would be the Young's modulus of this structure? And if there's a variation in Young's modulus, you run a finite element simulation, get the response of it. And so to do some kind of forward sampling or to reliability analysis to look at what would be the significant damage in there, or even global sensitivity analysis to look at the importance of different parameters that are there in these structures and so on, right? So so these are the kind of things that we wanted to eventually do, and let's say eventually be able to make some kind of engineering judgment in there. So most of the times, let's say structural engineers don't want to run, let's say, a CFD simulation that would take 15 days or a week or so. And but then if I talk to engineers from the fluid mechanics side, they're very happy. Now, a week is a normal CFD simulation for many of them, right? But then for a structural engineer designing a structure, they would want quicker responses. So kind of they want more faster solutions in there. Kind of that kind of makes it much harder to kind of bridge both the worlds in a way. But then we want to somehow bring in these things, and we want to understand this thing, and a very straightforward approach for us would have been to do forward propagation anyway. So we built in a forward propagation model where somebody puts in a different Young's modulus and runs takes the same fluid load, but is able to run the has the CFD solution, has a set of forces over time, a time series of forces, and is able to run the structural simulation in order to get some form of a response. But then again, a simple thing would be to run a simple Monte Carlo. But then we also made it allowed things for them to run Latin hypercube method, or even surrogate model multi-fidelity modeling in there to make it more numerically less expensive. Right? And so again, second thing that we wanted to do was to look at reliability analysis too. So one of the things that is of interest to a lot of natural hazards engineers is to look at reliability analysis. What would happen if when would a model, let's say, cross a particular threshold in a way? So I don't care about what would be the loads on the structure. What only I care about if it's going to cross a particular threshold. If it crosses the threshold, that's when my structure would probably be at a risk to damage or to break or to fail. And most of the engineers, structural engineers, want to understand that and want to reduce the number of simulations in a way. For example, let's say a 10% would essentially mean about 1,000 simulations. The 0.001% would mean about 10 to the power 6 simulation in order to get that percentage of let's say accuracy in a way. And that that's where we are looking at important sampling and subset simulations, and so even surrogate modeling, and a combination of both. These kind of methods have been incorporated into Hydrouq that would allow the user to, in order to run their simulations, put a structural model in there, and be able to do the reliability analysis and make a decision process to look at if it crosses a particular threshold. The last couple of things that are there in Hydrouq is one is to look at global sensitivity analysis. For example, if there's let's say, or all of these parameters equally impacting the response. For example, there could be the Young's models of the beam, there could be forces acting on the structure, and there can be variability in the structural geometry itself in a way. And how do each of these different variables impact, and which has a high sensitivity and which has a low sensitivity, to look at Sobol indexes and so on. So Hydrouq makes it very easy for a user in order to put these things in there and run their structural simulations, run the CFD, shallow water, and the structural simulation to do a global sensitivity analysis in a very, very straightforward manner in a way. And the last thing that is there is looking at surrogate models. Again, like here we have neural networks and Gaussian process that has been incorporated into Hydrouq, and something that we are working on is to looking at design of experiment to make it more easily accessible to the user, that they can run these simulations and do some form of design of experiments, including the CFD as well. So that kind of is our bottleneck in a way, to see how we can do faster CFD simulation. Shallow water runs very fast, but then the CFD is the bottleneck to get high fidelity in forces and a time series of forces in a very high fidelity manner. So people have been able to easily build surrogate models, and we are able to use that particularly on the structural side, either a one parameter system, two parameter system, or even a neural network, a Gaussian process, and so on. So one of the last thing that we recently have is looking at inverse UQ or Bayesian calibration, where looking at the simulation and looking at the force time series forces on the buildings, go back and let's say update the distribution after the observing the data in a way. So start with Young's modulus, but based on your simulation data, be able to update the Young's modulus distribution so that you're able to calibrate for the kind of structure, kind of forces and that are there on the structures, and observe based on observations and based on whatever your simulation model is giving, because there's a lot of uncertainty in there which we don't know about the structural response itself in a way. So again, like this has been used to calibrate material model, reduced order model, post-event damage diagnosis, especially because there's a lot of image that is available post-event to post-disaster that can be used. And can this be used to create, can we do Bayesian calibration in order to get the structural response and how the structure would behave in case such an event hit these structures in a way. So just to, I think hopefully I'm still on time and have there's some time for questions. So all of these things is available on the Naval Sim Center Hydrouq. So I would put the link to the master one where you have the most latest working version, I would say. So there are other beta versions that we are working on, but so you can, on the Navy Sim Center, on the link, you can find the Hydrouq software that should allow you to do all of these uncertainty quantification methods, not just you use UQ, but also be able to couple that with shallow water and CFD and finite element together. So I would leave this link with you, and I would be happy to answer any questions.
Wonderful. Thank you so much for the wonderful talk, Ajay. So let's have a Q&A sessions. So I don't see any questions in the chat. Yeah, but while you guys are thinking about the questions, I can ask some of the questions. You said you used the neural net model for the reduced model or surrogate model.
Yeah.
What sort of the neural net model? Can you elaborate a bit more on that?
Right. Yeah. So the Hydrouq has both convolution neural networks and RNNs in a way, because there's a lot of time series forecasting. So RNNs and LSTMs are there available, but also all of this is kind of open source. So if a user wants to bring in a different neural network architecture, they can add in and they can always push in. So the idea is to make it more community contribution in there. So one of the recent things that is still not available on the Hydrouq is the graph neural networks that we use. So where we were trying to build a surrogate model, not just for the structural part of it, but also for the shallow water and CFD part of it, where we use the graph neural network in order to let's say, run some of these CFD simulations and be able to train that. And that's where we were also working with Latin hypercube method in order to say, okay, what should be our next CFD simulation that we do that would offer us, that would span most of our space that we would want to in a way. So we combined Latin hypercube method to choose the next set of CFD simulations. And all of these was trained with a graph neural network to create a surrogate model. So there were two outcomes coming out of this. One was basically a compression in a way. So where one thing, I mean, this was a side, let's say, side effect of it, I would say. So all of these simulations were like, if you think of it, each simulation is like a Blu-ray disc, and you put everything into a pen drive, right? So that's essentially the idea that we wanted to put in. Can our graph neural network be trained on a lot of these CFD simulations in order to be able to replicate? I mean, essentially that's a surrogate model. And that was something that we were able to do very successfully in a way, both for CFD and for the shallow water solutions in a way. And a second thing that we were able to do was it's not just, you not just train it as a surrogate, but then now can you, for example, one of the biggest things for a lot of users on high HPC systems, when we are working with hundreds of processors, is to download this data. I mean, a very, very crude mesh here gave about 300 gigabytes of data. That's a very crude mesh, a bad simulation, I would say. So we were talking about terabytes of data in a simulation, and nobody wants to really download that to do the post-processing and things like that for it, especially if you want to create visualization. So what we did was to train the graph neural network with our simulations, and then you could download your graph neural network, save the network, and just download that. And you could train it at different accuracy. For example, let's say if I'm visualizing, I don't need to have 100% accuracy. I don't need a 6 decimal digit. A second decimal digit is sufficient for my visualization. So we were able to almost get 1,000 times compression because of that. In a way. So you say, okay, I need a 90% accuracy, which doesn't give me a 6th decimal digit, but just a second decimal digit. And that pretty much gave you almost 1,000 times, let's say, compression in a way. And you could just download that and use it for visualization purposes. So this is not yet put into Hydrouq, but this is the next thing that should hopefully go in the next couple of months. In a way.
Just curious, I mean, the graph neural network, the training of the graph neural network can be very demanding. And you said the data is huge. Probably training itself, it will be pretty computationally demanding. So but you put all the efforts, ahead, and then make it available to the public as a compressed.
So the idea was, what we did was to create like a sub process. So as the CFD simulation is running, once it finishes every step, there's also a sub process that is running, a parallel process that is running with it, which is running the graph neural networks, and that sends a message to the graph neural network saying that there's a new result available, and use that to kind of do the batch training with it. So each mesh is itself quite big. So each time step is broken into much smaller batches to do the training in a way. And there's also a bit of domain decomposition in there to not just train it as one single domain, but as multiple domains. So that way you can, before the CFD simulation runs complete, you're not completely training your graph neural network, but then you've done quite a bit of it already. And you don't have to train every single time step sometimes. So we kind of try to adaptively see if it can extrapolate and check for the error with the solution. And based on the error, it doesn't have to train that particular time step, but can skip the time step and go ahead. So that way you can save some time as well in a way.
Nice. So basically you guys do some dirty jobs for us, and then the users can take the data from the graph neural network in compressed.
Right. Exactly. So so basically the idea is essentially to make HPC systems easily usable for the users, so they don't have to download all the data, because this tool runs on the Texas Advanced Computing Center. And let's say somebody who's never used the HPC system can still use it because there's a nice interface to use this. So they just give a submit button and everything job submits there through an Agave API. But then, like once they say download, and now it starts to download everything, that would become a pain for the user to use it. right? So then they don't want to really use that. So it tries to download minimum amount of data, because everything, what happens is all the simulation data is now transferred to design safe. They can go to this design safe portal and from there access their account and get all the data that's run from the simulation. So it's a bit old way of doing things, I would say, but without criticizing that. So the how design safe works is basically transfers one file at a time from the tax system. I don't know, because I didn't build it, but somebody else has built it. So which kind of really slows down when you have a lot of files in a way. So you want to download everything as one single bunch in a way, and that kind of downloading a single neural network and just repackaging it makes it much more easier.
Okay, sounds good. Okay, so during the you mentioned the Latin hypercube for the sampling to
Yeah,
figure out the
right,
where
right.
to sample next time. Latin
Yeah,
hypercube is the predefined the design of the choice method. So, but there is a physics based sampling which
right.
can tell you where the maximum errors in terms of the physics, and then you can use information to determine where the next sample would be. So that might give you
Probably.
better way of sampling than simply
Okay.
using the predefined the Latin hypercube.
Okay.
Okay, so any other
Yeah, that's a good
question?
feedback.
Yeah. Any other
I think
questions?
Sergey has his hand raised, I think.
Oh yeah. Okay. Yeah, please unmute yourself, and then Sergey, you're welcome to unmute yourself.
I
And ask
thank
question, yeah.
thank you for very interesting presentation. It I have kind of strange question. Like information you're producing seems to be very important, and what you're doing to disseminate it, to give this to city planners, lawyers, which are like making decisions on like financing stuff, like building this vertical like shelters. I don't know how to say. There are also questions about predictions of earthquakes. It can be a similar method be used, etc. But and what I find striking, it was a nice slide about pollutions from cars. And if I get your slide correctly, pollution exhaust became kind of smaller factor than the other, which was kind of striking for me. So just I'm asking what you're doing to popularize your data. And I also see that like using this kind of simulation or analysis, making people to think again what factors are involved. And in many cases before, there was no clear models to take these factors into account. And now you can do it even like without having good physical model. And this is quite important to reanalyze all existing models and factors and find missing factors. So what you are doing about like to popularize this idea. So, okay, sorry for this long question.
No, you broke up a little bit in the middle. Yungsu, were you able to catch all the question? I mean,
Oh, just
I
well,
don't know if
briefly,
my
what you have a lot of interesting data, important data for people, for lawyers, and for city planners, etc., for
right.
governments. What you are doing to popular to make them known to public, to wide public.
Right. Okay. Yeah. So yeah. So I think Sim Center has its own way of publicizing things. I mean, now I'm not officially with the Sim Center. So one thing that I'm doing also in the UK at the moment is trying to work with some of the city council here in Manchester in the UK, and also there's a consortium called CCPWSI Plus. So it's called the Computational Center for Wave Structure Interaction. So where they are also looking at the tsunamis and storm surges and these events. and we are trying to work with let's say, so one of the industries that we are looking at is to look at if this would be interesting to some insurance industries, especially those who are doing like reinsurance and looking at insurance in hazard areas, particularly that could help them really make a better assessment of what are the events that could happen in here, what is the real risk that is there that could really reduce some of the premiums that are being charged in a way. So we are trying to work with some of the insurance companies and also with city councils and city planners, to see how we can bring these tools into their design process and into their decision making process. uh, but the difficulty is that it's quite hard because eventually there's a lot of uncertainties in the system, so that kind of makes it really hard for them to, let's say, take a decision based on these tools. But there's very concerted effort trying to get it to them in a way and trying to get them to do it. So one of the recent things that I myself started was to look at debris. For example, UK recently released a report that said that we don't really have any kind of database of what could be the debris that comes during these flooding events. So most of the damage that happens is not just because of the water, but because, for example, let's say assume there's a car that is floating in and that blocks a building. Now the water that has flowed is not able to flow past the car, so kind of the water level builds up a little bit around there, and now that adds more loading onto the structures in a way. So we don't really have a, let's say, a database that says, so this is the kind of event that happens, these are the kind of debris that are coming in, and so on and so forth. So we are trying to build a, let's say, use YouTube videos and post hazard videos to do object detection to map out what are the kind of events and what are the kind of debris that would come in because of these events, and how do we use that in our physical simulation to not just look at just the wave but also to look at the debris. So that would give us a much more, let's say, more robust, let's say, evaluation of the structural response in a way, more in a way. So so there's a lot of a concerted effort going to get this into the hands of the city planners and structural engineers, and also particularly with regard to also insurance companies and so on. But the progress is, I would say, reasonably slower than what we would like. Uh, we would, of course, like them to immediately integrate into their design philosophies, but I think that takes more time. I think it's that we need a more concerted effort there.
Yeah, yes, thank you very much. I understand what you're doing. That it is interesting example. Like shell company scientists were doing their own climate prediction model,
Right.
which appears
Yeah.
to be quite accurate. And nevertheless, shell company was doing what they were doing. Yeah, they were doing the same stuff. And
Yeah.
so you are making, say, a product which insurance company can make. And then I can rephrase my question. Are you considering to like bring this information to climate activists, not only to companies,
Yeah.
so they can affect government and companies?
Yeah.
Okay.
Yeah. Yeah. So we because the problem is extremely multifaceted, multidisciplinary. We also we try to reach out to the geophysicists and let's say climate scientists and people who are in the, let's say, geological area in a way, kind of, let's say, I would say, who are looking at more like the things like sedimentation, erosion, and all of these things as well, and climate change, what sea level rise as well, to see how this can also be incorporated into their workflow. Biggest problem is some of these simulations that we do are very local in a way, right? So even though we can do a large scale simulation, we are more focused on, let's say, a building, or like let's say tens of buildings, or for example a critical infrastructure, maybe a nuclear or a chemical plant or something like that, which is around the coast. So it's more local than looking at the global infrastructure itself. Uh, so uh, this still, uh, we are reaching out to them, but then I think they are looking at a different scales. So there's still a bit of, let's say, a mismatch in discussion. So one of the biggest things that we are trying to do is firstly to reach out to, let's say, academics and faculty, even in the humanities area, because they look at post-disaster event, how do communities, let's say, let's say how is the damage changing after these damage happens? How do communities, what do you say, come back to normalcy? I would say I'm not getting that word, but then let's say that they have a disaster, they're all displaced now, they have to come back to their homes, and how much time does it take for these things in a way? So even this would be our very first step to see if we can make the change there, so that this amount of time that people need in order to come back to their homes can be reduced in a way. So if you can, let's say, take a community and predict the kind of damage that could happen depending on the events, can you improve the resilience of the community? Can we make it better so that they are less affected over time because of these events and so on? But then yes, there's a effort to reach out to climate scientists and those who are modeling sea level change. But I think then we need to start communicating in the same language. I think both the communities need to start talking in the same language. I think that's where there's a bit of a mismatch at the moment.
All right, that sounds good. Okay. If Sergey, if you have a more questions,
Thank you very much.
Yeah. I guess you can ask Ajay. Send an email, and then Ajay will be happy to answer you.
Yeah.
There's another question by Jeremy, and he asked, you mentioned building a digital twin for aiding in making decision. Is your twin comprised of the surrogate or the full order model? That is the intent of the twin to be used in real time? Is the twin and the decision making with the twin aware of the uncertainty you are quantifying? Yeah, those are the questions.
Yeah. So the idea of building these digital twin is essentially comprised of both the surrogate model and also based on the actual full fidelity simulations. We essentially I forgot where I put that. Yeah, but then we essentially don't want to just limit it to the surrogate model, but then we also want to have full fidelity. On a structural side, we don't have much of a problem with running a full fidelity because most of these structural models are made of beams and plates and structural elements which run reasonably fast. For example, you can run like each simulation probably takes like a few seconds, maybe at most. Your very complex building simulation might take a little longer, but we can run a full fidelity simulation. We don't necessarily need a surrogate model, but having a surrogate model allows us to span a whole bunch of space and makes it much easier to look at it in a way. So you can run either both a surrogate model or a full fidelity model. Yeah.
Okay, sounds good. Okay, next question is by Alan. Oh, well, no, it was not a question. It was just, he was thanking you for the great job. Okay, is there any other questions from audience? No? Okay, well then, let's thank our speaker Ajay today for the wonderful talk. And if you have a, the additional question, please email Ajay directly. I think he will be happy to answer you. And also, if there is any collaboration opportunity, please reach out to Ajay. So Ajay, you're looking for collaboration, right?
Definitely. I would be very happy if anybody has any questions or would be interested in collaborating. Then there's a lot of opportunities in this area. There's a lot of open problems, and I would be very interested. You can also look. My lab website is ajaylab.co.uk, and you can also find my email there. Or also, I think this email is maybe there on the invite, and I would be very happy to work with you as well. And if you're interested, yeah.
Wonderful.
Thank you so much.
Well, thank you so much for the
Thank you so
wonderful
much
talk.
for the wonderful opportunity.
Okay.
Thank you. So thank you so much. See you then. Yeah. Bye.
Bye.